PLC Chapter 2, Hardware Components. Let me get it started over here. The I/O section. You know, we've talked about earlier that the PLC basically makes decisions on the physical, real-world electrical signals that come in and out. So we're going to talk about the I/O section. We didn't cover this last time, did we? Okay, just checking. Some of the screens look familiar. So, okay. But this is what you read, Chapter 2, right? Okay. So the input-output I/O section of the PLC is where everything gets connected. Now, there are two types of inputs, okay? What you see here is commonly referred to as a shoebox processor. The I/O is fixed. There's nothing that can be done about changing it. If you have something blow up, all you can do is program around it until you run out, and then you throw it away and get a new one. Now we have modular types that use external I/O like these, and these cards simply slide in and out. And we have a few examples here of some different ones we can pass around. They simply slide in and out. All right. What's more expensive? The ones that are interchangeable, they cost more. Do they perform any better than the small MicroLogix? No. In fact, I should have a small MicroLogix somewhere, but we have these shoebox processors up here. Yeah. Some of the MicroLogix 1100s are expandable. So, okay. Now, rack-based I/O, it's made up of individual modules. Input, of course, accepts signals from the outside, while outputs convert the program signals to the physical world. Okay? We're all pretty, no questions about that. Okay. The hardware that houses I/O module, that's commonly referred to as a rack or chassis. They come in different makes and models. This kind of the logical rack is addressable by a unit consisting of 128 input points and 128 output points. That kind of goes back to the old PLC-5 days. It depends. That's really not accurate for some of the ControlLogix and stuff, but that is all set up in configuration, so we're not going to delve too much into it. Just if you have an 8-slot chassis, how many cards can you have? You can have 8 cards in that one, since the processor is dedicated to the first one. And depending on the card, is how much I/O you can have. So 16, 16, 16, so forth and so on. So, a lot of times, if you're making a big control system, it's very inconvenient to run the wires a long distance. Because first of all, the price of copper is so high, it is cheaper to buy the hardware and the communication cable than it is to buy a giant bundle of wires and run them across the plant. So what we do is we have a say, a central processing unit, and then all the little different sections it controls, they will run the communication cable to another remote I/O. Okay? Now this is, if it's a high-speed application, a lot of times they won't do this, but if it's like a conveyor system, you know, we don't care if there's a tenth of a second delay in a conveyor system from reading I/O and stopping a motor, unless, of course, you're moving stuff at 200 miles an hour, and I guess that would be the exception. But normal box conveyor system, we don't care about a little delay. So we use, basically, we have a processor here. We run through some kind of communication channel, and then we go to another remote I/O processor here. And here's a little sample where it says stop, start, motor, and here we come back to, we're reading the input of a sensor, and we have an on and off control of a hopper. Now, I bet you didn't know that you can even do this with inverters. The PowerFlex drives, if you buy the enhanced version, there's some extra I/O over there. You can even read the status of what's there. So it all, pretty much they all come with it. But the enhanced version has some outputs that will handle 24 volts, that you can have a drive, and you can have a manual override start-stop station attached to that drive, right? Well, that override station is actually going back to the PLC, and the PLC decides, well, hey, the system's not in e-stop. Let's say my e-stop is halfway across the plant. Then it's okay to run this in manual, you know, or there's feedback. You can make those buttons do anything you want to. Once you get your signals into the PLC, you're only limited by your programming. Does that make sense? You can do whatever you want to. It's all a matter of programming. That's why we like it. If you make a change and it doesn't work, you can hit the undo button while they're running and change it back. And then more than likely it'll be a mess in the process, but it's a quick test, right? Otherwise you'd have to shut them down, power it down, unwire, rewire. It's a big hassle. So now, the memory system, it stores all the information, all the inputs and outputs, and it keeps track of this, and it uses a form of addressing, okay? Now, basically an address is a label, a tag, as in the case of ControlLogix, that indicate a place in memory, okay? And we're in the SLC system, what we're talking about, we have some predefined data types, and that inputs and outputs have to go in input and output tables. And that's pretty much a given for any PLC, is there's predefined spots in memory for this stuff to go. Rack slot based addressing, those are the schemes that are used with Allen-Bradley's PLC-5s, 500s. ControlLogix are tag based, and if you take some of my advanced classes, we'll talk all about tags, but I will say that tags are basically names you make up, okay, and you can point them to anything you want to when we're talking the new stuff. For an example, anyway. Let's go on to, here we have a PLC-5 rack slot-based addressing format. Basically, we have the first one is either I or O. It says it's either input or output. The next one is a file number. This is for PLC-5. The next one tells you the card and the slot, okay? So let's look at this one right here. This is input card 1:0/0. All right? That makes sense so far? And if we look at some cards, if we were to look at a PLC, well, we can just walk in here and look at them. It won't take a second. We'll try out the fancy webcam and see how it works. Maybe it'll connect. And That's okay. We got time for me to play with stuff. Not too big a hurry. Oh, I think it just started working. Let's see if we can switch over to it. And here we go. All right. So, what we're looking at over here, let's just say, for instance, that we wanted to look at input 1/0, okay? So what we would do here is we have an Allen-Bradley processor, and what we're going to do is slot 0 is here. So this is 0. We want to look at 1/0. So then this is 1. This is slot 1. All right? And it's an input card, so it's going to start I:, slot 1. And if we want to find 0, it says it right there. It's the first terminal. So the very first terminal on this card is I:1/0. And that's our address. Does that make sense? If we move it here, the first one would be, since it's an output, it'll be O:2/0. The next one would be O:, or I:, because it's an input card, 3/0. That makes sense? All right. All right. Well, I don't know if it recorded or not, but that's okay. We tried. So let's go back to screen share. And recorded something. Anyway, recorded my voice. All right. And we just explained this for the 500 series. When we're talking PLC-5 series, that gets a little bit confusing. I don't have one to show you, so it's a little hard for me to explain it. But we're going to concentrate on the SLC 500 series. And this is what we just did. Okay. So, every input and output module connected to a discrete. And now what does the word discrete mean? You hear that? You're on, off. Thank you. Discrete means on and off. Analog, you either got discrete input or analog input. Discrete is it's either on or it's off. Analog is some kind of signal that varies. And there's a varying degrees of on and off, basically. So, here we have discrete input. It's showing that the input is addressed to I:1/0, which you just looked at. It goes into data files. All right, it just at the start of the program part of the scan is read the inputs, put them into the data files, scan the program, at the end of the program, take the output into the scan, take the output, move it into the output data file, and then move it into the output address. Turns the motor on. So it goes through here all like this, really, really fast. Multiple times a second. All right. Now, analog I/O uses a little different. It uses a word addressing format. Okay. So it's not going to have a bit part. Okay, of the address. It's basically going to use the whole word. So let's look at a little example here. This is input :2, and they usually put a little dot 0. That's for thermocouple 1. And that would be channel N1, all right? So this is a analog meter output, and it's output :2.0, which is channel analog output 0. This will be labeled right here on the inside of the card. Almost all of them have a label. If you don't fit on the card, the door falls off, you get the manual, it'll be on there. And then right here, if we had this another input, you know what that one would be? It would be I:2.1 right here. So if we showed another input here, we'd simply count down as we go down the card. Basically, as you go down from the top to the bottom of the card, pretty much all Rockwell PLCs will increase in the channels. This one happens to be split, so halfway it switches to outputs, and once we get to an output, it starts over to 0. So, ControlLogix, on the other hand, use a tag-based. What this stands for here is pretty simple. Local means it's attached to the PLC in the local slot somewhere. If this was a remote rack, it would say whatever name you gave it. Does that make it confusing yet? You could call, I usually name them remote racks, but you could call it remote rack 1, or you could call it depends on what you name the I/O. You can change the name. Local is a constant. That's a given. Can't change that. But you can change the name of your remote racks. So, and then :6 indicates card 6. Okay. :1 indicates, well, that's not a good ideal right there. Should be local : that should be an I or O. That looks like a little mistake there. So it should be card 6. Yeah, this is not right. Of course, I didn't make these PowerPoints. We'll get into that before we get out of here. I'll have to pull this up, and I can't do it right now. But basically, the data .0 is the bit. This is the slot. This should be a designator saying with an O or an I. Okay. But we're working on SLCs, but I'll show you that before you get out here. That's not a big deal. Now, has anybody ever heard of a system called Opto22? A lot of times in the early PLC days, they actually had PCs. If you've seen one, it more than likely runs DOS and is covered in dust and has a green and black screen. But they have actual PC-controlled PLCs. Sometimes they are also known as soft PLCs, and basically they have built-in I/O. Now, Allen-Bradley sells one called a ControlLogix, and it will actually run an entire plant. It doesn't have any I/O, but it can link to physical I/O across Ethernet and run stuff. And the only time those should ever be used is for data collection, because to depend on a Microsoft operating system to run 24/7 is not a good idea. It will crash and it will glitch, and then your plant's down. So ControlLogix are pretty much for testing and maintaining data collection. Okay. Now, some of the old systems that use like Opto22, they had a dedicated old-school DOS computer that run constantly. That was great. What I'm referring to is when we get above like XP and Windows 7, don't ever count on those to run 24/7 for years on end. Sometime or other, they're going to glitch. Basically, I tell people, if you want a PLC, buy a PLC. If you want a computer, buy a computer. Don't try to mix them. Now, we talked about combination I/O modules. We saw that. earlier on the analog cards. Typically, you will only see these on analog cards. This one here is showing a little bit different. They do have them, but they cost so much, it's cheaper to buy 2 cards. What they do is they cost so much is because people expand their I.O. and they don't have a big enough rack, and they get down to the very end and they go, man, we just need 6 more inputs and 6 more outputs, but we can't expand our rack. And so then they'll charge them like 3 times the normal rate for this one little card because they don't have any choice in the matter. They have to, anyway, they're expensive. More expensive than a standard input and output card. So let's look at an I.O. module made up of a printed circuit board. The printed circuit board contains electronic circuitry, and it has a terminal and status lights. Now, I'll pass one around over there, and you can kind of look at it. But when a light comes on, usually on the input card, that means that input's on. Let me tell you something. If the input, let's just say you have an output card, and the output light's on, but the output doesn't work. Well, if you put your meter on it and you don't have anything coming out of it, that means your output's burned up. You know, these older ones, they didn't know that. The output light still comes on, but the physical hardware inside that card's burned up and it does nothing, no electricity comes out of the terminal. In which instance you change the card or you change the programming to something else. Okay? So, let's go look at this next one. Now, in order to save time wiring, a lot of places, if you have to run to a terminal, you can buy these extra. And so if you see one of these on a PLC, don't flip out. All they're doing is pulling the I.O. If you look on the one I handed you here, these 2 screws come loose. This whole assembly slips off, and they'll slip a new quick connect cable in there. And it's just because they sell them in predefined cables, and they run down and spread out the terminal blocks. A lot of times they're all quick connect, and they run down and have fuses already built in, and that'll be a quick way to distribute I.O. Okay, I.O. points, they come in 8, 16, 32, and apparently somebody makes a 64, but I've never seen it. If you have a 64-point I.O. card, you're going to have a plug for it because it's physically impossible for anybody to put that many terminals in that small space. And I expect anybody to be able to get in there and wire it up. So, discrete. What does discrete mean? On-off. On-off. Okay. Discrete I.O. on-off consists of stack lights, relays, motor starters, indicator lights, inputs, selector switch, limit. Okay, we're broadcasting again. Here we go. We talked about discrete output module schematics. Let's talk about size, okay? One thing you have to remember on these outputs, and especially on some of them, is that for smaller PLCs, the outputs are like half an amp. And that might run a small relay and it might run a small contactor, but it will not run giant, old-style contactors that take 1 and 2 amps to pull in, like a 50-horsepower motor. It won't run those. So in that case, you have to insert relays in the circuit to run the larger loads. You get where I'm going. You can overload these little relays, these little outputs quite a bit and blow them up. I mean, that works for a little bit, but after a while you'll start blowing outputs and it gets to be really expensive. Even though you do have them fused, that if you got to be careful. Some of the smaller remote devices are like half amps, and everybody puts a 1 amp fuse in them. Well, of course, that's overloading them. They'll work for a little while. We have to watch that. And you're going to ask me how I know that? From experience. From having to go back and put relays in. You have to watch that. So, here we have some examples. We have a transistor output load for DC. We have triacs for AC. And we have relay outputs. Most people prefer either relay output modules because they don't have to worry about what they hook to them. The back side of that is they wear out faster. If you want long life, you're going to buy semiconductors. If you want high current and flexibility, you'll get relays. But, you know, I don't know what the life expectancy is. It just depends. You can find out, but relay lasts a really long time. Let's look at this one. So, certain I/O modules specify whether the module is designed for interface with current source or current sinking. Okay, notice it has a DC power supply. Now, if the module is current sourcing, then the input-output device must be a current sinking. That makes absolutely no sense, does it? Because I would show you easy way to explain sinking and sourcing. You have to give me a second to pull up I have a special PowerPoint I must find. That pretty much explains it all. And once again, these are all available in that Google Drive account that I gave you on the first day of class. Okay, here we go. This may just be about as easy to drag over there. Stop this slideshow. We're going to go through this here for too long. I just want to show you this one part while we're talking about it. And it is at the very end of the slide. Okay. Make sure we're broadcasting that, which we're not. Okay. What we want is positive logic when we talk PLCs, okay? And, you know, I hear syncing and sourcing, it becomes a little confusing, but we want positive logic. If we put a 1 or we flip a light switch, we want the PLC to say, that's on. If I put a 1 in an output, if I give it a 1, we want to call 1 on. We're binary. We got 0 and 1. We want 0 to be off and 1 to be on. If I put a 1 bit on that's tied to an output, like output colon 2/1, if I put a 1 in that place, I want the output to come on, don't I? That's positive. So let's look. So what we want is we want syncing inputs and sourcing outputs. You can buy cards, and a lot of German machines are wired with negative logic, which means they switch to neutral. They don't switch. Well, we can, of course, AC, but they'll switch the 0 volts. They'll switch to neutral on the contactor. And the contactor will always have a hot wire on it, and people will put their meter on it, and they can't figure out why is it not going off. That's because they're switching the neutral for a lot of German machines, and that's just how they do it. So let's look at this. So we want syncing inputs, right? So here we have the positive from our battery. It comes up to our switch. This is a button, and it comes into our card. All right? And that's positive. The common is tied to ground. There's your key. I want my common tied to ground. All right? On input. However, on outputs, here, well, my common needs to be my incoming voltage, right? If I want to put 120 volts to the card and switch it going out to all my outputs. All right? So the common here is negative, but the common here is positive on the output, and that is our sourcing output. Does that make sense, Steve, to describe the difference? Most photo eyes have a wire you can flip to change how they work. So you have a normally, but it goes back to normally open, normally closed, light operated, dark operated photo eye. A lot of them they come when you buy them, they've got 4 wires. You know, you've got a hot, neutral, and you've got syncing and sourcing output. Positive logic. Okay. So we're going to go on to the next one. Sure. The what? Well, that's just a type of transistor and how they work. And NPN is typically what they use. I will get this backwards, so don't quote me on this, but like NPN for syncing and PNP for sourcing, just the type of transistor. So we'll get into that in another chapter, because we'll go over that. I've got some diagrams on that. So but just say that that's a different type of transistor, and one works one way and the other works backwards. Does that make sense? I'd have to refresh my memory all to get backwards. So, analog I/O modules. All right. Well, an analog I/O module. Let's kind of look at this. We have a level transmitter. Through the level transmitter, we go to a analog input module, we go to the processor, and go to analog output. Now, analog inputs and outputs vary from 0 to 20 milliamps, which is standard. Okay? And the reason we use milliamps is because over long distances, we can transmit amperage, whereas we don't account for voltage loss. All right? If we try to transmit voltage across a long distance, we're going to lose some of it. But they have circuits that push amperage, so we read the amperage. Amperage is going to up the voltage or decrease the voltage. It's a little electronic circuit. So we can just keep it in your head that milliamps can be transmitted over a distance, more so than voltage, because we'll get a voltage drop. Typical things are 0 to 20 milliamps, 4 to 20 milliamps, or 0 to 10 volts. 0 to 10 volts are fine for a short distance. If you try to run them all the way across the plant, it won't work. Now, when we take an analog signal, all we're doing is we are converting 0 milliamps, and we're calling it 0. And then we have what's called a range or a resolution on our card. And when we have a 20 milliamp, this is our signal coming in or even going out. When we have 20 milliamps coming in, depending on what type of card and the resolution, we'll get a number in the PLC of 16,000. And so we don't know what that means, right? Other than it says right there, if you want to know, on the card it says when you get a 16,000 on this card, then you have 20 milliamps. We have to scale that into a value. All right, like 0 milliamps is 0 degrees, and 20 milliamps is 16,000, which equals 100 degrees. Does that make sense? We'll have to scale that into a usable value. But the main point at this point, I'm not getting into that, is all analog signals, when they're an analog, there's an infinite range of possibilities. Once they go digital, it's going to convert it into a number between 0 and 16,000, or 0 and 4,000, or 0 and 32,000. It all depends on the card, the resolution of the card. So there is a limit, right? Because when I say there's an infinite range in an analog signal, I mean we can have 4.222 to the power of 10th milliamps. Okay? Does that make sense? Well, once it's converted digital, we're going to get 4,022. That's just an example. We won't get 4,022.5. We're going to get 4,022. So it's basically the same principle as a CD. You know, everybody complains about the difference between an LP, how it's an analog sound and it sounds better than a CD. A CD basically samples the waveform. If you have a wave, this is all we're doing here is we're sampling a waveform. So basically, if we have a waveform, we have a signal. I'm just using a waveform as an example. How we do it here is this is analog. We have infinite range. Well, when we do a sample, we're taking, well, where's it at here? And where's it at here? And we do that 44 kilohertz. Yeah, 44,000 times in a second, which is CD quality. And then we play that back to the human ear, and it can't tell the difference. Does that make sense? So we're just sampling. And that's why we have a range. Okay. Still broadcasting. We're doing good. Doing good. Let me pull up the next one. Okay. So, there's two types. We got voltage sensing and voltage current. We just kind of hit on that, right? So we're either going to sense voltage or output voltage, or we're going to output current. All right? A lot of times, that's determined by a jumper on the card. So a lot of times, cards will do both. And you pull the card out, or sometimes it's even in the PLC configuration on a ControlLogix. You flip a switch and it works with voltage. You flip the switch, it works with analog, or you hook it to a different input on the terminal. They'll have three terminals. One is for voltage and one is for current, but they both go to the same place in the PLC. Does that make sense? So they'll have three terminals for an input. You'll have a ground, and you'll either have a voltage input or an analog current input. Now, when we talk bipolar, that means that if it's bipolar, it can accept negative values. So basically what that's saying, if it's bipolar, we think of a battery having a positive terminal and a negative terminal, right? Well, bipolar means that they can swap and it'll start counting down. It'll go negative. So the positive terminal becomes a negative terminal and it falls below, and the negative terminal becomes a positive terminal. So it goes on this range. Does that make sense? Once it flips below, it drops to 0 volts, and then it's just reading potential. Unipolar means it only reads 0 to 10 volt positive. Okay? And we talked about resolution just a little bit ago, so we've kind of got that down, I think. For the most part, you understand where I'm going with resolution. That's just the amount of sampling it can handle in the card. So typically, old SLCs were 0 to 4,000. SLCs are about, there's an exact number like 16,384. I don't know what it is. I can't remember off the top of my head, but SLCs are about 0 to 16,000. The ControlLogix, since it's 32-bit processing, is 0 to 32,000 and something. So, now, unlike voltage input signals, current signals are not as sensitive to noise and typically are not distance limited. We kind of hit on that already. One thing I want to point out here is sometimes we have what's called a looped power supply. And here, I want you to look at this. Pull the mouse over here. Here we have a battery, and it goes to a sensor. Okay? And this sensor outputs a positive and negative, or 4 to 20 milliamp loop. And it comes over here, and it reads it. Right? And it works. These are easy to understand. But that means that I have to run 2 power wires and a ground to that sensor, okay, when I run the wires. And sometimes, like in the case of, I'll give you an example. Sometimes sensors pull more power than 4 milliamps, and we have to do this. And I'm going to get into loop power here in a second, but let's just say if ultrasonic sensor is a good example, that it'll pull about 1 amp on some of them. Okay, which is a lot, which means that it has to have its own dedicated power supply. So, the reason we have 4 to 20 milliamp is typically old school, you know, the PLC will read 0 to 20, right? 4 milliamp was 0, because if you read a 0 milliamp, that means the wire was broken. And you could sound an alarm or make something happen. So the standard was 4 milliamp, because 0 basically said something's broke. Now, let's look at this loop power. And this is a little confusing. But basically, we put a power supply, we take the positive wire, and we go to the positive. Each one of these will have it in the manual. We go to the positive on the sensor. And then we take the negative back to the PLC. And then we hit the negative to the power supply here. Now, you ask why you do that. Because I only have 2 wires going out to my sensor. The only way you can get away with that is if the sensor pulls less than 4 milliamps. Because what it does is the sensor has little electronics in it that say, I pull 2.3 milliamps, but I'm going to put a resistive load in there to make sure that I always pull 4 milliamps on this load. That way I won't confuse the PLC, right? So if you have a sensor that pulls 4 milliamps, it's always going to pull that. Does that make sense? It's always got to pull that. So it says, hey, I'm here and we're at 0. And then, of course, it's going to vary the load depending on the temperature, pressure, whatever kind of sensor it is. But it's loop powered. It only has 2 wires going to it. Now, they have meters. Used to, if you read amperage, you have to disconnect the wire and hook your meter in the loop. Well, they have newer meters will actually read the milliamps across the terminal. You don't have to unhook any wires. Unless, of course, it is a loop-powered device, in which case it's a dead short and it blows the fuse. You will know this happens because the fuse will blow and it will hear a slight pop and everything will quit working. So be aware of that when using your meter, that some meters, you know, we want to check voltage. We put our meter across the terminals. We do that with a loop-powered device, and we set our selector to milliamp. With the loop-powered device, it will pop a fuse. Anyway, because you're basically shorting positive to negative. That's the power supply. Over here, it can read these. It cannot read those. So you have to pull the wire loose and connect the meter in series, which means one lead goes to one terminal, and wherever you pull the other wire off goes to the other terminal. And that way you can read that. Okay, let's go on to the next one. The main element of the analog output module is a converter. That's what takes the analog signal and turns it into a number. I don't really know what else to carry on to about that. I think we've kind of beat that to death. Are you with me on analog and digital? How the conversion? That's a digital analog converter. It's just a little chip, and it's built into everything. And you'd be surprised the number of stuff that has it built in. A lot of audio equipment. My Bluetooth headset that I'm wearing right now to record this has one built in it, because it's taking the analog sound through the mic, converting it to digital format, transmitting it across wirelessly to this computer where I'm recording my voice. Okay, so it has one. We're using it right now. Analog I/O control system. Here we look at a way that the valve is initially opened at 100% as the fluid level in the tank approaches the preset point. The processor modifies the output, which adjusts the valve. This is basically a PID loop example, but they're just showing how an analog input comes into the PLC, the level. Depending on the level, the analog output with the aid of the PLC programming controls the valve. Does that make sense? So we're looking for 0 to 10 feet. If it gets a little low, we're going to open the valve up. If it gets a little high, we're going to start closing the valve down. It's an analog control variable. Special I/O modules. We have what's called high-speed counter modules. And what these are used for is usually some kind of servo for positioning or measurement, and they have very fast electronics. Basically, high-speed counter modules have a little brain inside them, because the PLC can't keep up with it. Okay? But it'll keep up with a number that's stored in there, and every once in a while the PLC will go out there and get that number for the count. And if that count is, 2 inches, and then when it makes it back around, it might be 2.0001 inch, or it might be 2.002 inches. It doesn't keep up with the number. The card has smart electronics and everything to keep up the number for it. Does that make sense? All it does is that happens so fast, it's basically a little brain keeping up with its own number, and the PLC will, every time it scans, it'll come by and grab that number. For the most part, the precision is so far off that if we miss counting from 0.001 to 0.002, who cares? The card's doing it for us. We're just going to read the status every once in a while. Typical count rate available is 0 to 100 kilohertz, which means the module would be able to count 100,000 pulses per second, which is a lot of times faster than what the PLC, depending on the program, can ever keep up with. But it can go out there and grab that number every once in a while. Thumb wheel, I hope you never see one. Basically, what a thumb wheel switch does is we have them out here. I can even show you one because we have them. Let's see if my camera is working. I'm scared to touch this thing, but we'll give it a shot and see if we have a broadcast going on. We'll stop and then we'll connect it. And we got a failure. Like that. Sometimes you spend more time working with technology than you do using it. But we really want to record this, don't we? Yes, we do. So we're going to take time out and make it work. And I think we're up. And let's see if this works. Boom. Oops, get my finger out of the way. Here we go. On to the next room. We'll see what this does. So, what we have here is an analog thumb switch. And what that thumb switch does, I want you to watch the numbers. See this card right here? It's tied to 4 inputs. Oh, that's a bad switch. There we go. And basically, it's a little cam and switch system that counts from 0 to 10 in binary. And it uses 4 inputs. It's counting in binary with just inputs. Does that make sense? It's basically, it's taking 4 inputs and translating them into binary. And there's special coding in the PLC you put in there to make sure that it does that. But we just use 4 inputs per switch. It's kind of wasteful. There are even scanners that use more. I've seen old. This is the old tech. Hopefully you never see one of those. Now we use touch screens and we just type the number in on a touch screen and it magically appears. That's a thumb wheel switch and that's how it works. It's basically a gear and cam rotary switch that's made that when you put a 0, it translates 4 inputs into a binary number and turns them on the appropriate way to the PLC to read it. So, anyway, let's go back to our PowerPoint. Cool, I think that one works. There we go. And we're back. That's a way to talk transistor logic. I've only seen those in junk piles. Hopefully you never do. But basically it'll talk with 5 volts. And you can, anyway, we're not getting into that one. But it's really old. Hopefully you never see one. But it'll basically talk in 5 volts. Encoder, that basically is a module that you'll see these attached to conveyors and different things, and all it is just like a mouse. You're using an encoder. Oh, I'm using a touchpad, but if you use a wheel mouse, not an optical mouse, but the old school wheel mouse with a ball that always got dirty and you had to take out and clean it, if you ever took one apart, you'll see a little wheel in there with little holes in it, and the holes go through a photo eye, and every time you move the mouse left or right, it counts, and that translates into the mouse position. That's an encoder. Now, of course, they have different types besides that, but that would be a simple optical encoder. Basic ASCII modules. This is specialty modules that you can write programs, and you can tell it to run ASCII module 1 to control the robot. Those are, you just about have to have the programmer or descriptions to troubleshoot those. That's pretty old school. Now, in the ControlLogix system, we can buy special interface cards where they sell robots that the robot programming is done in the PLC, not in the robot. The PLC is the robot brain, and all the robot is a slave to the PLC. Typically what you'll see on any of these applications, though, is the PLC will turn on an output or send a bit. It'll say, run program 1, and the robot will go to program 1, and then it'll go, all right, your part's in place, now run program 2, and the PLC will send that signal to the robot, and the robot will move its arm or cut or whatever to program 2. And that's usually how that works. You get where I'm saying? They're two separate entities, and the robot will usually take a cue from the PLC because the PLC controls when the part's in place to work on. Stepper motors, those are a little difficult to explain, but basically we do some pulsing and we'll control the motor. All right, we'll pulse the motor, we'll pulse 2 outputs and the motor will turn a little bit, and we'll pulse it again, 2 more, and it'll follow around. So those are typically found in printers. We don't use those quite a lot anymore. Okay. These are old displays. The same way the thumb wheel switch worked, where we translated 4 outputs into binary, we can do the same thing with a outputs. We can translate those outputs, and this will display them for us. We use touch screens anymore, so we simply read the data in the PLC. We eliminate all this physical stuff. We just read the data in the PLC and translate it to the touch screen. PID module. If you buy a PID module, then why'd you buy a PLC? Because PLCs have PID instructions. But you can buy pre-built PID modules. Motion and position, there are servo cards, specialty cards to read the position of a servo motor and control it. Serial communication cards, here we have a touch screen. All right, have a touch screen and some different stuff, and that all depends on what you're talking to. Hopefully you're using Ethernet, not serial, for a touch screen. It'll be kind of slow, but it works. I/O specifications. Here we talk about nominal input voltage. That means the amount of voltage it takes to consider itself activated. Okay? That means we talked about 0 to 24 volt input card. Well, at 21.3 volts, it will say I'm on. Or some of them will say at 12.6 volts, I'll say. That's the nominal. Input threshold. Specifies the minimum on-state voltage at which logic 1. Oh, I'm sorry, that's the threshold voltage. Nominal input voltage is the amount, is what is the minimum it's designed to accept. The threshold voltage is when it switches from 0 to 1. Current per input, if you put too much current on input, you can blow it up. That specifies the minimum amount of current the device must be able to handle to push the PLC card input into action and make it work. Ambient temperature rating, just like it says, if it gets too hot or cold, it quits working. Delay time, response time, how quick it reads the signal and translates it to the PLC. Output voltage, that's what the card's made to output. Relay, we talked about, can do a lot of things. Be aware, though, DC will arc, whereas AC won't. So DC is bad about arcing. If in some weird instance you're trying to switch 90 volts DC through an output card, it will work for a while until it arcs so much inside there it burns it up. You have to be careful of that. I don't know why you would want to switch that, but DC will arc more than AC. And there's special considerations that you need to take. For the most part, we don't worry about it. Output current, we talked about that. Inrush current, well, inrush current specifies that when you first turn something on, we have a quick surge of current, like that it can handle short spikes, so you need to make sure that that stays low. Short circuit protection, we actually have output cards that have built-in electronic fusing that if they're pulling too much current, they'll shut off and sound an alarm. The PLC will fall. And that's pretty much a lot with ControlLogix. But I've seen them actually, the cards have tiny little fuses in them, and you got to pull the card out and find them, and those are horrible. But they actually have them built in. Leakage current. We just looked at leakage current when we looked at the triac and how it was leaking 20 volts when it was off, right? I should tell you right there, that's leakage current. Electrical oscillation, we talked about optical oscillator. Points per module, that's the number of I/O on the card. 16, 8, 32, 64, that's how many terminals, how many points of I/O. We can hook 16 push buttons to a card, or 32 push buttons to a card. Backplane current draw, what you have to do is, depending on your power supply, and this is done, you can do it manually, just adding up, but if you do it, there's a way to do it in the program. It shows you, you tell the program what cards you have in there or what cards you're going to add, and it'll automatically calculate the wattage because it's stored in the software, and say your power supply is undersized, it won't handle it. You need to buy a bigger power supply. So we talked about that. So basically it just says the watts, like a hairdryer, with a hairdryer, or talk about electric heater. You got 800 watt or 1200 watt electric heater. Well, if your power supply is only let's say you have a 1200 watt electric heater, but your power supply is only 1000 watts. Will it work? No, because it pulls more wattage than it's able to deliver by the power supply. So basically you add up the wattage of all your cards, check the wattage of the power supply. If it's over, it's good. If it's under, it's bad. Most of the time you got a little leeway there, so it's not exactly precise. I would say if you had a 1000 watt power supply with a 1200 watt draw on, no, I'm not talking electric heaters, but we're talking like PLC cards, you're okay because it'll never pull. That's only if all of them were turned on at once, and that'll probably never happen. Channels per module, that's the same thing as inputs per module. Current, voltage ratings, input protections. Usually you're not going to hurt analog signals if you tie the wires together by accident or hook them up backwards. There's protection on those. Most devices are that way, and some devices that are that way aren't. I've seen that before. Resolution, we talked about resolution of analog, input impedance and capacitance, and we're going to worry about that. Common mode rejection, noise that is picked up equally in parallel is rejected because the difference is 0. That's why we use twisted pairs. Let me explain this to you. If you have, this is actually how Ethernet works. This is the way we're able to transmit wires for long distance data. Because let's say you have serial, which is not, it may be twisted, but we don't consider it twisted pair. But let's say we have an Ethernet cable, and it's 0 to 10 volts is a serial cable. But we use an Ethernet, and Ethernet says that, I don't remember the exact voltage. Ethernet says that if I see a difference of 5 volts between wire 1 and wire 2, then that's a binary 1. If I see a difference of negative 5 volts between wire 1 and wire 2, that's a 0. Well, the pairs are twisted, so when they're running the ceiling and they pick up stray voltage, they both pick up the same amount of stray voltage. It's differential. It's looking for a difference in the voltage. It doesn't care if it sees 10 volts, probably up to 24 volts or 13 volts. It's looking for a difference in the wires from the source. Does that make sense? Because whatever's sending the signal is going to send out a, let's just say this computer A sends out a signal of 5 volts. And the time it runs across a fluorescent light up here, it picks it up to 12 volts. But there's 2 wires, right? They're twisted together. So they both picked up the same amount of volts, which was 5. They both picked up 7 volts. So over here on PC2, it comes over here and it says, oh, well, I've got 12 volts, but I don't care because the difference between them is still 5 volts between the 2 wires. So wire 1 that had 0 volts now has 5 volts, and wire 2 now has 12 volts, but I'm going to subtract those and say, oh, there's a difference. I'm just counting that as a 1. All happens really fast, but that's the premise behind differential wiring and how we can account for electrical interference. You got me there? You feel me? Little? Yeah. We don't care about the voltage. We care about the difference is the same. So the difference is the same at the start as it is at the end. And since they're twisted together, if they pick up some stray voltage, they'll both pick up the same amount. So they'll both pick up the same interference, but there'll still be that difference. Right? Okay. CPU, that's the brain. Let's just look at these. Basically, we talked about it. SLC is a Game Boy. ControlLogix is your smartphone. That's how far different apart they are. Same thing in your computer. I don't think we have to beat that down. It's the brain. We have two sections. Power supply, you have the processing unit and the memory, communication interface, and I/O modules that go to the data table. That's pretty self-explanatory. In reality, you watch this and you're not going to troubleshoot a CPU. It either works or you throw it away and get a new one. That's the basis behind it. PLC power supply, we already talked about that. CPU, same as what in the computer I'm recording this on. Now, fault-tolerant PLC systems support dual processors. What that means is in, like the ControlLogix, if you want to pay enough money, you have two brains running the same program at the same time, and if one of them screws up, the other one picks right back up and runs. And usually what happens is we have a user program, right? And so what it'll do is processor 1 will scan the program one time, and then it'll tell processor 2 it's your turn. So they'll alternate. So every other process scan, they'll switch back and forth. All right, and this is all behind the scenes. Nobody knows it until processor 1 says, hey, processor 2, it's your turn, and processor 2 goes, either I'm not there or I'm faulted, and processor 1 says, okay, well, I'll take your turn and sound an alarm. And so the system runs, and everything's great. Nobody knows anything's wrong. An alarm is set on the panel view, and that's all great and good, except nobody pays attention to it till 6 months down the line when processor 1 fails in a really bad system like maybe heat treatment. They lose thousands and hundreds of thousands of dollars of metal are ruined because they didn't pay attention to that. But that's beside the point. Processor 1 and processor 2 work in tandem, and if one fails, it picks up right where the other left off. You never know it. Okay, we talked about how a key switch runs a processor. You either have, most of the time you want to leave them in remote, which means that the remote computer can say if they're running the program or they're in program mode. When it comes to Allen-Bradley, green lights, solid green lights are good. Flashing green lights usually means maybe communications or status. Flashing red lights means something's bad wrong. If you see a flashing red light, something's wrong. That's pretty much universal. Flashing red, sometimes just solid red, but on Allen-Bradley, if it's flashing red, something's wrong. So, electrostatic shield your stuff. I've never really paid attention to it, never had any problem. Monitored semiconductor doping accounts for that. I've never had any problem, but you're supposed to. Memory design, here it just simply talks about how much storage, and I want you to pay attention. The MicroLogix typical has 1K. That's not even a floppy drive. The old giant floppy 5 1/4 that were actually floppy disks were 512K, right? So they had the memory of 512 of MicroLogix. And they have 64K, and then we got 32 megabytes. Big difference there, isn't it? So 32 megabytes by our standards of your smartphone is, that's not very good. But I remember when I paid $50 for a 64 megabyte flash drive, and that was pretty good on sale. Memory location refers to an address in the CPU memory. But we kind of talked about that. We're going to be talking about 16-bit processing, so there'll be 16 bits per word. Let's see where we're at on this PowerPoint. I'll overshoot myself. We've got other stuff to cover here. Pretty good on time. Okay. Sections of the memory used to store the status of the inputs are called what? Input status files. Things that you use to store the output, they're called what? Output status files. Remember where that goes back to, we told you that the inputs are stored into the input data table. And the input data table is read by the PLC and used in the program. When it gets to running the program, it writes the data to the output data table. And from there, the output data is written to the card. There's a reason for that. One of the reasons is forces. And we'll get into forces in our exercise. But input data simulation, we can't do that one. I don't have the files for that. Here's the same thing for the output. Memory types. Okay. Non-volatile memory has the ability to retain stored information when the power is turned off. All right. Volatile, it's violent. You kill the power and it's gone. So, used to, that's why we have little battery backups for stuff. The newer ControlLogix and stuff, they don't have batteries. It's just built in. It's like writing data to your flash drive. When your flash drive sits on the table for 6 months, it still has the data on it. It doesn't have a battery. Okay, but used to, we had to worry about the types of memory. And SLC-5s, you pull the battery back up out of them for an hour, and they'll discharge and lose the program. That's a given. Here's ROM or read-only memory used by the PLC for the operating system. That's basically the behind-the-scenes stuff that we're not concerned with. That basically says when I get a binary or a hex or some kind of instruction, that actually means it's a normally open instruction. So we have a higher level of programming that we're going to be working with. That's the operating system. Here we talk about batteries and how if you change the battery, you lose the memory. This, I hope you never see one. Used to, on really old stuff, they would store the memory on EEPROM chips, and you wouldn't have a computer to download. You would have to have an EEPROM burner, and when you got ready to erase the EEPROM, you'd pull the little piece of black tape off and shine a light in it, and it would erase it. Then you'd put the black tape back on it and use your EEPROM burner, burn it on there, pull the little chip off, carry the little chip over to the card, pull it out, slap it in there, and hope you didn't break something along the way in the process. We don't use those anymore, but there's what that is. I'm not going into EEPROM because I hope we never see one. If you do, it's so old it's probably time to throw it away anyway. Flash card. That's the same thing as what's in your camera. That's what's in those up there. They got a flash card in them. Just a way to store memory on an SD card. Actually, one thing about the ControlLogix, that has a device net, which is a type of communication network. You can actually ghost that entire system, including drive parameters, device net setup. You can basically, just like you take a computer and you ghost a hard drive, you can ghost that system. And if you have something bad happen, you can go in there and plug up stuff. And if everything works correctly, it might take about 10 minutes, but it will go out there and rewrite your whole network and your drives and fix everything magically. I've never tried it, but it's supposed to work. Programming terminal devices. Hope you never see one. Would you like to see one? Because I have some. Oh, no. Did you see that one in there? No, I saw that one. Yeah. Yeah, that's why we have computers. We don't want to use those. They even have them. I've actually had to use them that were little green monochrome schemes that had cassette tape backups. Like audio cassette, like you put it, those were where you stored the program. Yeah, that's bad. I've seen them. Here's what we want. We want a laptop computer with a serial port or Ethernet or wireless or something. Recording and retrieving data. You can print data, all right? Not a big deal. You can print the PDF. You can just open the program and look at it. I think we pretty much got that we program with a computer, don't we? Any questions about that? We type in the computer and move the mouse, and we know what we're doing, something happens. All right. Some PCs support the use of memory cartridges, and they actually, ControlLogix sell, like we used to have a pre-built system that we didn't let the customer make changes to because of FDA regulations for a medical device. And if there were upgrades or changes, we would send them this box. And this box had a button. And we would load our code. They would plug it into the processor, hit the button, and it would magically download the program, and then they would send the box back to us. Okay? Or they have little chips. That's kind of what they're showing. And they cost a lot of money, and they don't serve much point other than that. HMIs, that is a touchscreen, or a PC running the HMI software where you click on it with a mouse. HMI stands for Human Machine Interface. This is what we want. If I need a button, I make one. I don't go find one, knock a hole in the panel, and wire it up. It's much simpler. In fact, I can make the button while they're running if they don't mind having the screen blank out for just a few seconds in the meantime. You know, if I have an Ethernet HMI and they say, oh, we need a button to do this. All right. Are you where you can, I'll wait till they go on break, and when they come back, they got their button. All right, I don't have to do anything. I just make a button on the screen. The button's tied to a memory location in the HMI. When they touch the screen, it takes that one and says that one goes to the PLC in this location. PLC sees that and does whatever. Just use binary bits. Plus, I don't know if you've ever seen those, but look on that screen right there. Do you see the nice display to make a graphical user interface? The old graphical user interfaces required a large Star Trek, original Star Trek looking board that was, oh, I don't know, very large and had small LED lights on it. And each one of those LED lights was tied to you would have half your rack just running the display. Okay? Those were really, and if a light ever went out, when you opened it up, there were massive amounts of solid. These were all custom made, by the way. So we like graphical user interfaces so the operator can tell what's going on. You can even insert pictures. And so you'll have a picture of the machine, and if there's a problem, there'll be a little flashing red light and an arrow pointing to that picture on the machine, and the operator will go, oh, that door's not closed, and they'll push the door closed. Right? So that's why we like HMIs. Hey, that's the end of it. Are there any questions at this point? Okay. Had enough. All right. Well, I'm going to stop this broadcast.